through this stuff so you can get working. A couple quick problems here. I want to look at, so we looked at this stuff yesterday talking about complex impedance has a real part and an imaginary part. And we were looking at a couple examples. Like let's check out example, let's do example B. Okay. So if we do example B and we want to add up the impedance of this circuit, Z is our impedance. Now, what is going to be the contribution of that 12 ohm resistor based on that chart? Well, it's, if a resistor has, as an example, if a resistor has an impedance of 3 ohms, then the impedance of the resistor is 3, positive 3. So it's 12, right? So if this is a 12 ohm resistor, the impedance is 12, okay? How about the 8 ohm inductor? 8I. So we're going to add to that 8I because we're taking the sum of the individual impedances to calculate the impedance of the series circuit. These are in series because they're all in order, one after the other. And then finally, how about this guy, the 15 ohm capacitor? And we end up with an overall impedance, if I add up like terms, of 12 minus 7I. Good? Okay. All right, so that's a detailed description of the impedance of this circuit. If we want to just know a number, though, how hard is it to drive electricity through this circuit? We calculate what's called the modulus. It's written, it looks like absolute value. When we write something like the absolute value of a complex number, it's a little more involved than just absolute value. A lot of times people will call it absolute value, but that's really not correct. It's called the modulus. And it's always equal to the square root of the real part squared plus the imaginary part squared. So for us, that would just equal the square root of 12 squared plus negative 7 squared, which is, what is that? 4, so that's going to be 193, square root of 193. Whatever that is, that's just some number, right, that we could calculate, and that's going to give us the value of the modulus. This is going to be a number. It's going to be roughly, what would that be? What is that going to be? So 14, it'd be just about 14-ish. I think it's like 13.9, something like that. I think that's about right. Somebody look it up real quick. What is it? If you just do somebody got a calculator, just do, what's the square root of 193? 0.89. So it's close. I mean, so it gives us there's a decimal approximation of what the resistance would be in ohms, okay, of that circuit. Okay, so it gets a little more complicated when you deal with circuits that are in parallel, meaning there's more than one path that the current can take, right? So if we look at example B here, look what happens. The current could pass along branch 1 or it could pass along branch 2, right? Make sense? Yes. Yeah, there is going to be a problem like this. Yeah. So but don't panic. This is really, it's just all it ends up being is just a formula that involves some computations with complex numbers, just some, arithmetic with complex numbers. So here's the formula we use to calculate the impedance of a parallel circuit. The formula is it's equal to the product of the impedances of the separate paths divided by the sum of the path impedances, right? So we would call, if path 1, we're going to call this path 1 and that path 2. Well, the impedance of path 1 would just be the series impedance of those two elements added together, right? So let's calculate Z1. Z1 would just be this guy. Whoops. What's the contribution of a 5 ohm resistor? Okay. And then this guy, 3 ohm inductor. So there's Z1. Z2 is going to be new colors, this guy.
No, wrong problem.
Oh, wrong problem. You're right. Wrong problem right there. So that's 8, right? And then what else we got? Minus 9i. Okay. So the overall impedance then Z would just equal the product of the impedances. So 5 plus 3i times 8 minus 9i divided by the sum. Okay, so what's that give us then? We got to FOIL the top, exactly. So on the top, if we FOIL that out, let me rewrite that. That's going to be too hard to see the whole. Okay, so bottom is a piece of cake, right? What's the bottom going to be? Okay, add like terms. Top's a little more involved. Okay. Okay, on the top, we're going to have to FOIL. So if we distribute the 5, we're getting 40 minus 45i. If I distribute the 3i, okay, what's this one going to be? What's 3i times negative 9i? Which is 27, isn't it? Everybody get how we get 27 on that last one? The I squared turns to a negative 1, right? Negative 27i squared is positive 27, okay? So if we combine like terms, then we get, what is that, 67 minus 21i over 13 minus 6i. We done? No, we're not. You're right. No i's in the basement, exactly. Okay, so we've got to take that result and do what? How do I get rid of those i's in the basement? What do I do? Multiply by the complex conjugate of the denominator, exactly, right? So we're going to multiply by 13 plus 6i on both the top and the bottom. Again, the bottom is easy. It's what squared plus what squared? Plus, yeah. That's our complex conjugate product pattern. A plus bi times a minus bi always equals a squared plus b squared. Okay, that's easy. Top, we've got to do a little bit of distributing again. So 67 times 13. Yikes, that's going to be 871. There you go. 871. If I distribute this, I'm going to get 360 plus 40, so 402I. Okay. If I distribute negative 21I, that's going to give me, what, 130 plus another, what is it? Yeah. Negative 3. That's not right. 21 times 13?
Yeah. Negative 21 times 13. Negative 373. That does not sound right.
That can't be right, because 21 times 10 is 210.
It is 273. Yeah.
You said 373?
No, 273.
Oh, 273. Oh, yeah. I was going to say, there's no way that's 370. And an I, yeah. I thought you said 373.
I was like, but it says
Yeah, yeah.
Just get going.
Yeah. And then negative 21I times 6I, that's 126, plus 126, right? Okay, so if we combine like terms, what are we getting here? On the top, 871 plus 126 is 997, correct? You guys, everybody agree with that?
Yeah, 997.
402I minus 273I is 129. Yeah, 129I, right? So, okay. And on the bottom, 169 plus 36 is 175. Is that correct? No, what am I saying? 169. It's going to be 195? No, 205. 205. Okay. So is that how we want to write it?
No, simplify.
We want to what do we mean by that? Split it up, right? We want to split it up into separate fractions. We want a real part and an imaginary part that are separated. So we get 997 over 205. And that is undoubtedly not reducible. Yeah. Yeah. Plus 129 or 205. I don't think that's reducible. So that's our answer. Okay. That's our exact answer. Now again, if we want a number, just a single number, right? We want to calculate the modulus of that impedance. Being as you guys have those fancy calculators handy, let's calculate that. So our modulus would equal the square root of 997 over 205 squared plus 129 over 205 squared. What's that give us as a decimal, roughly?
Oh, wait. Hold on.
5 point something?
4.90.
4.90. Okay. So it's about 4.90 ohms would be that's how hard it'd be to drive current through this thing. Okay. All right. Make sense?
Wait, hold on. Don't even scroll up.
Okay. Okay.
Yeah.
Are you recording?
I am recording, yeah.
Literally could watch the video.
Okay, I got it.
Okay. All right. So, okay. So then This is what we call the complex plane. Okay, the complex plane, look what this is. It looks just like the XY plane, doesn't it? But the horizontal axis, instead of being the x-axis, we call it the real axis. And the vertical axis, instead of being the y-axis, we call it the imaginary axis. And so ordered pairs in the complex plane, here's what this would look like. If we had the complex number z equals a plus bi, that would correspond to the ordered pair AB. So now you see why the imaginary part does not include the I, right? The imaginary part ends up being the y coordinate of the complex number when it's plotted in the complex plane. Okay, and the other thing that's really cool about this is, like, just in general, look at this here. I'll show you a quick picture. So if this is the real axis and this is the imaginary axis, and we've got the point out here with coordinates a, b, so that corresponds to the complex number a plus b times I. Good? Okay, what we a lot of times do, we, instead of just having a point in the complex plane, when you do talk about this stuff in college, you'll talk about that as being a vector. A vector is just an arrow where the tail of the arrow starts at the origin and the point of the arrow ends up at the point that defines the number, right? Ends up at AB. Okay, so if I break that up into a right triangle, wouldn't this just be, this is the x coordinate, right? So that is the length of that base of this right triangle I'm building is just going to be A. Everybody agree? And the height is just going to be B. And this represents the modulus, right? By the Pythagorean theorem. Because isn't the modulus, by definition, just equal to the square root of a squared plus b squared? Isn't that what we get from the Pythagorean theorem? Right? Right? A squared plus b squared just equals modulus squared, right? Everybody see that? Right? By the Pythagorean theorem. This is a right triangle, isn't it? So don't we have, for a right triangle, don't we just get, here, I'm just going to write it this way. So the modulus squared equals a squared plus b squared, leg squared plus leg squared equals hypotenuse squared, right? If I just square root, then I get the equation that ends up just being really the distance formula. How about that? That's really cool, right? So the complex plane, all this stuff comes together in the complex plane. These are the coordinates of the point, and the distance from the origin represents the modulus. Okay? What's that? Oh, okay. Okay, I'll get that in a sec. So what about this one over here then, right? So does it make sense that this would be the point corresponding to the complex number 3 plus 2y? Because that's the point with coordinates over 3 and up 2. Does that make sense? Okay. Where is Naomi? Oh, okay. Okay, well, can't give it to her. Okay, so I got a couple quick practice problems. Super easy. I just want you to see this. These are the kinds of problems you'll get on the complex plane. Really basic introductory stuff. Yes. Well, that's what we do. You can do it. Okay, so how about this one? All you're supposed to do is just plot that point in the complex plane. What would the coordinates be? So over 6, up 8, right there. Done. Easy, right? Okay, what would those coordinates be? -5, -6. How about those? 0, 6. Yep. Okay, how about those? 1, 0. There you go. 1, 0. Okay. Yes, we got it. Easy. Okay, that's that stuff. Yeah, it's going to be on the third homework. Third homework. No. Okay, the rest of homework 3 is stuff like this. Okay, so stuff like this, where this looks familiar, right? The only difference between these equations and the ones you did in 4.3 is that these ones are going to involve square roots with negative radicands. That's it. But now we know how to deal with that, right? That just involves complex numbers. So what would the steps be? What's my strategy for solving this one? Okay, because I'm isolating x. I can point to a single x, so I can isolate it with inverse operations, right? So if we add the 8 to the other side, we get x squared equals negative 72. Then we square root both sides, right? And that cancels the squared, and that's good. Then we get x by itself equals, if I square root both sides, what do I have to include? Plus or minus, right? If I square root both sides of an equation, I have to include plus or minus. What does the negative inside the square root become? An I outside. And then I just have to simplify the square root of 72. What's that going to be? 6 square root of 2. Yeah, right? Because I can break it into 36 times 2. Perfect. So we end up with 6 plus or minus 6 radical 2i. Okay? 2 answers. Okay? How about this guy? And I want to cheat just a little bit here. Let's do, oops, that's not what I want. Let's do this. I want to get rid of, I don't want that negative sign to be there. There. Okay, how's that? Again, what's my strategy? Isolate x. I can point to a single x. So what's my first step? Subtract 4. Okay, if I subtract 4 to that side, then I get 5 times the quantity negative 2x minus 2 squared equals negative 162. Now what? Divide by 5. Okay, those guys cancel. So I get negative 2x minus 2 squared equals negative. But we don't want to do that. We want to leave it as a fraction. Reduce the fraction if possible, but we can't. What's next? Square root. Okay. Okay, that's good. We get a negative 2x minus 2 equals, what do I have to include? Plus or minus. Okay, because I square rooted both sides. So I've got a plus or minus. We know we're getting an I outside, but we do have to simplify this other part. We need to simplify the square root of 162 over the square root of 5. We can split it into separate square roots. Okay, 5 is already simplified. Can I simplify the square root of 162? What would that be? Say it again. 9 radical 2, right? Because half of 162 is 81, which is a perfect square. So 162 is 81. So I get a 9 when I square root that. Radical 2 over radical 5. but I haven't simplified the whole thing yet because there's no tenths in the basement rule, right? So what do? Okay. Okay, so then I end up with on the top 9 what? Square root of 10 over 5. Okay, so then I get plus or minus 9 radical 10 over 5i. Okay, almost there. Now what? Add 2. Where am I going to put the 2 on the right side? Before the plus or minus. Okay, so those guys cancel. And now we've got negative 2x equals 2 plus or minus 9 radical 10 over 5i. Last step, divide by negative 2, which is fine. However, because I already have a fraction on this side, what might be more convenient than dividing by negative 2? Yeah, multiply by negative 1/2, right? Let's instead of dividing by negative 2, why not multiply by a fraction? It's easier to distribute a fraction than it is to distribute denominators, I think, right? Especially when you already have a fraction there. So we will just multiply the whole thing through by negative 1/2. Okay, when we distribute that, negative 1/2 times negative 2x gives us x. That's the whole point, right? Okay, so we get an x. When we distribute to here, negative 1/2 times 2 equals negative 1. Okay, when we distribute to here, if I multiply a negative times a plus or minus, how do I treat that? I don't even need to worry about the minus because I already have both a plus and a minus, right? So I'm still just going to get plus or minus. And then 1/2 multiplying this fraction by 1/2 just gives me a 10 on the bottom, doesn't it? 9 radical 10 over 10i. Good? Anybody see that? Okay, so those, I mean, all I did, I just multiply straight across, don't I? 1 on the top, right? 1 times 9 radical 10. Okay, makes sense? Okay, so now I want you to notice something here. I get, how many solutions are represented there? 2. What is their relationship? How would you describe the set of those 2 solutions? They're complex, but you could say something more about them. They fit a pattern. Negative 1 plus 9 radical 10 over 10i and negative 1 minus 9 radical 10 over 10i. What does that seem like? Okay. Well, no, I don't mean that. I mean, what do we call a pattern like this? Aren't they fitting the pattern? Doesn't that look like the pattern A plus or minus BI? So what are those? What's the word? Come on now. What's the term? What's the vocabulary? You got to talk like a mathematician. Complex what? Conjugates. That's it, right? Okay, so that is not an accident. This is really important. We're not going to deal with this so much right now, but very shortly, we're going to take great advantage of this. Whenever you end up getting solutions, when you solve an equation and you get a complex, you get a solution that's a complex number, this is crazy, but it can never happen in an isolated example. You can't get just one complex solution. They always have to come in complex conjugate pairs every time. There's no other way, right? So, for example, a linear equation could never have a complex solution, and it couldn't, right? Where are you going to get an I out of a linear equation? It's never going to happen because you don't have to square root anything, do you? Right? So linear equations could never give you a complex solution, but quadratics could, because there are two solutions to quadratics and only one solution to linear equations. Okay, I'm jumping way ahead there, but just kind of keep that looking into the distance. That's where we're going with this stuff. But for now, you don't need to know those are complex conjugates. You just need to be able to find both of them. Okay, give me 1 to 5. How we doing? Okay, work.